This video is going to give you a fantastic overview of the Web3 concepts shown on screen. Let's start by taking a look at the concept of a wallet. Just like a username and password controls the ability of a person or entity to access a particular system, a blockchain wallet controls the ability of a person or entity to access a blockchain. Reading data stored on a blockchain does not require any authentication or a wallet, but if you want to edit data or execute code on top of a blockchain system, you will need a wallet. Like typical username password authentication mechanisms, you have the concept of a username or ID for each account on the system, and a password which can be used by each account holder to prove that they are the person that originally created the account, assuming that they never share or compromise their passwords, of course. A blockchain wallet works just like a username and password and is comprised of two parts: a public key and a private key. The public key acts like a username and is a sequence of characters that identifies each account that uses a particular blockchain. I keep saying particular because there are many blockchains. The private key acts as the password for the account represented by the public key. A private key is a sequence of characters just like the public key, but you'll often see the private key transformed by various algorithms into a sequence of words called a seed phrase. Seed phrases allow humans to more easily remember their private keys. Because humans are prone to picking usernames tied to personal profiles and passwords that can be easily guessed, the Web3 approach to account creation generates both usernames and passwords on each user's behalf. Web3 usernames and passwords, aka public and private keys, are not determined by user input, but instead are auto-generated for each user via military-grade cryptography. Because Web3 account creation relies solely on the math underpinning these cryptographic algorithms and not on any internet-connected systems, account creation can actually be done offline and does not rely on any third parties. This is fantastic for protecting private keys, as private keys never need to be connected to the internet for users to use a blockchain. When a user wants to use a blockchain, however, they must provide a digital signature derived from their private key that will be used to prove to the operators of a blockchain that the data associated with a public key has been approved to be changed in a particular way. The digital signature algorithm used by most blockchains is called ECDSA. Once again, your private key does not and should never leave your computer or be shared with anyone except yourself. So as we were saying, if someone wants to read the data on a blockchain, they do not need to be authenticated or have a wallet. But if they want to edit data on a blockchain or have a blockchain execute code on their behalf, they will need a wallet in order to supply two things. One, a digital signature derived from the private key of their wallet to prove to the system that an action that affects their account has been approved. And two, a small amount of cryptocurrency that depends on the blockchain being used. The small amount of cryptocurrency alluded to in point 2 is paid by users to the operators of a blockchain and is how the operators of the computers running a blockchain system are financially compensated for their service. Each node on a network of computers running a blockchain system performs the same tasks as all of the other nodes on the network, the most important of these tasks being storing copies of the database holding user data and processing user requests. This means that even if a node or a group of nodes were to reject or deny your requests, as long as you could find at least one other node that would accept and process your requests, you could still use the system. This is because the state of the blockchain network or the database is kept in sync across all of the nodes via algorithms called consensus algorithms. This consensus feature of blockchains is what gives them their decentralized quality. But it's important to note that this consensus feature only works when there is a sufficient amount of independently operated nodes on the network, the exact number of which depends on the exact consensus algorithm used by that particular blockchain. Each blockchain bakes its own cryptocurrency into its software so that the amount of usage each user can subject the system to is capped. Each user can only store as much data and only execute as much code on a blockchain system as the amount of native cryptocurrency they own, and these limits apply for the node operators as well. After a user uses all of their cryptocurrency, they must then provide goods and services to the other users of the system in exchange for more cryptocurrency and the continued ability to write data and execute code on that system. Now let's run through a few Web3 terms, starting with the concept of a dApp. A dApp is an application just like any other application, except that this application uses a blockchain to store at least some of its user data and or process at least some of the requests that users make while using it. User requests that are sent to the nodes of a blockchain and that result in the nodes making some update to its blockchain database and or executing some code are referred to as transactions. I've been using the term user requests and or transactions a bit loosely up till this point, but here is the definition of a blockchain transaction. I have also been using the term blockchain a bit loosely as well. The only part of a system that we refer to as a blockchain that is actually a blockchain is the user database. All other aspects of the systems that we call blockchains, for example, the wallets, cryptocurrency, consensus algorithms, node operators, etc., none of those aspects of a blockchain system have anything to do with the technical definition of a blockchain. A blockchain is a database, or to be exact, a data structure. A database, for those who don't know, is a system used for reliably storing and accessing data over long periods of time. Most databases found on the internet nowadays are referred to by the Web3 community as centralized databases because they allow the companies, and typically small groups of leadership at these companies, full reign to edit and read whatever data they want. This includes the ability to shut down accounts, modify user data without consent, restrict user permissions, etc. Users whose data resides on centralized databases typically have little to no transparency on the data that sits inside of them. In contrast, blockchain-based databases level the power dynamic between users and operators by 1, allowing anyone who interacts with a blockchain database to read all stored data, and 2, only allowing users and operators the ability to edit data for which they hold the private keys, assuming a sufficient number of independently operated nodes on the network, of course. The mechanism for how this works is by processing at regular intervals each batch of requests that users send to a particular blockchain network. Each request or transaction sent with a valid digital signature gets stored into a data structure called a Merkle tree. A Merkle tree will store user data into leaf nodes and will build parent nodes comprised of the hashes of its immediate children, eventually resulting in a root hash code. When you take a Merkle tree storing a batch of user requests or transactions and combine it with a set of header fields containing the root hash of the current Merkle tree and the hash of the previous batch of transactions, then you now have what is called a block. And the term blockchain refers to the fact that each block is connected to the block preceding and following it via these 2 hashes in its header. Changing any user data in a blockchain would have a cascading effect that would ripple up the chain and easily allow other nodes on the network to detect that a malicious node had been tampering with data simply by reading the hashes in the header of the malicious node's last block. I'm getting the feeling that this has gone way too technical, so I'll leave it here for now and collect feedback on which topics should be expanded upon next. Bye-bye.